Hello, everybody. We are Team 14, the frame and mechanical drivetrain team for the Fluid Power bike. Before starting, I want to preference that there are two teams working together on this project.
Our goal is to provide our team members with real-world engineering experience and to contribute to the club's legacy of innovation by driving advancements in fluid power technology based on enhancing efficiency. We will design a mechanical drivetrain that works with the vehicle's hydraulics, pneumatics, and electronics so that we can compete in the National Fluid Power Association Fluid Power Vehicle Challenge.
As mentioned before, we are competing in the NFPA Fluid Power Vehicle Challenge. You may be asking what the Fluid Power Vehicle Challenge is. The Fluid Power Vehicle Challenge is a national competition sponsored by the National Fluid Power Association that challenges engineering students to design and build a human-powered vehicle that incorporates fluid power technology. Teams from universities across the country compete by developing a functional vehicle that balances efficiency, power transmission, and performance. The final event includes technical presentations and a dynamic performance test where teams showcase their vehicle's capabilities in areas like speed, endurance, and efficiency. The project is a great opportunity to meet industry professionals in the fluid power, mechanical engineering, and manufacturing industries.
Our vehicle can be divided into four separate subsystems, these being the mechanical system, the pneumatic system, the hydraulic system, and the electronic system. The mechanical system can be divided into the frame, steering, and transmission. The pneumatic system encompasses the regenerative braking system. The hydraulic system involves the regenerative braking system as well as the boost system, and the electronic system involves the control system and the HMI. The scope of our work is to design, build, and test the fluid-powered vehicle, which will enhance performance over traditional bicycle designs. We'll also lower the vehicle's weight while maintaining efficiency. And integrate fluid power systems into this human-powered vehicle. We will optimize the bike's design while remaining within the competition rules, and the team does not plan to modify the existing vehicle, but rather to create a new one throughout the course of this semester.
Our design goals center around improving the vehicle in a few key areas, as the previous vehicle was pretty successful in competition. The key areas to improve, as stated previously, are in the reduction of overall weight of the vehicle, more controlled and robust steering components, and a new internal hub to ensure the reliable power delivery to the vehicle. The reduction of weight on the vehicle is done so primarily through the change of the frame from aluminum extrusions, very dense and very thick aluminum extrusions, to quarter-inch wall thickness aluminum rectangular tubing. This choice saves on weight, but at the expense of modularity, as obviously it's much harder to adjust placements of components with something like aluminum rectangular tubing. But this problem will be mitigated with extensive planning. One of these ways will be in the complete CAD file, or in the complete CAD design of the bike, which will ensure that we at least have a guide or something to go off of when time comes to drill holes and attach components. So one special thing we did this year to ensure that the bike would have a substantial enough frame was doing FEA with the frame. As seen on this slide right here, it is the shear diagram for the stress on the frame. It's well within the limits of the aluminum that we're using, and especially with quarter-inch wall thickness aluminum, we never expected to have any problems with this, but it was good to do the FEA for this just to ensure that our designs were sound and that the bike wouldn't have any issues. And for the next graph, it shows the total displacement of the frame, and each one of these arrows right there in the middle, and there are 6 arrows in total, are each 50 pounds downward, and the most displacement in the bike frame will be 0.1 inches, which is about 1/100th of an inch, which, if I'm correct, is like a 64th of an inch of displacement in the vehicle. So the substantiality, I guess, of the frame really does not come into question. And just as a further way to ensure safety, for the next graph, there is we did a factor of safety calculation for this, and it is almost 10 times. It has a factor of safety of almost 10, which is almost 10 times the industry standards. So, lastly, for vehicle design, the steering design of the previous vehicle was actually very good and was nearly perfect in theory. My additions to the vehicle came in the form of a different geometry of the handlebars, thrust bearings on the steering axle to improve ease of use, and brake discs on the front wheels to improve the stopping power of the vehicle. The Ackerman steering gives the vehicle a more agile steering design, where the inside wheel has more aggressive turn, or has a more aggressive angle to turn, as the radius is much smaller than the outside wheel. However, on the real bike, the spindles were very flimsy, and the Ackerman steering was functioning the opposite way as it should, causing a lot of problems in the competition. A new, more robust spindle and a more favorable geometry was added to solve this problem.
All right, with the new sort of design here, we had to make it new custom in-house spindles, just for future wheels and such. Since last year there was a problem with the spindles, like we stated before, just being flimsy and not very reliable. So this year we're just making them in-house, and the design kind of is pretty heavily based on the OTK spindles, so the Tony Kart spindles. Just since they fit pretty well with what we need, and they can be designed for an IS mount with the disc brakes, so that'll go along pretty well. As well as fit 15 millimeter sized hubs, which is what our wheels are going to be using this year, just along with the disc brake mounts. And then we have a video demonstration of just what we have inside our capstone. We've got our bike frame here, like Bro mentioned earlier. This is the pedal mount. It's going to be drilled in and tailed down. I'm just trying right now, but this is what it will look like when it's fully drilled in and assembled. Spaces here for the spindles. These will be cut out, and they'll be kind of like a built-in C-channel housing for them. Here we've got some wheels that just came in today. These will be built, or maybe mountain bike tires. They're 27.5-inch diameter wheels, built in for those with the 15 millimeter hubs with disc brake mounts that'll be used for our two separate braking systems. And then there's the transform as well, and the names. And then over here, we've got our Shimano hub that we're using for our transmission. It's a continuous variable transmission, so it'll change gears as we go. We've got our mount for it, so we can actually power it up. Do you have the battery for this?
What?
Do you have the battery for this?
The battery? Yeah.
So we actually have the controller for it, so we'll be able to actually get a reading on its speed and as well as its gearing. And then using this, you can go up or down on the gearing, so shift it. So here, a little demonstration. So inside there, right there, so you can shift up, shift down, like so, and that allows us to shift in our gears. So that's what we have so far. Rest is being built. Should be ready for a proof of vehicle the next month. I think that video pretty much covers a lot. Basically what we've already said before. I did forget to mention about the wheels being 27.5-inch this year, as well as just having large mountain bike treads. So on that. So for our cap, here's the references we got, just 2 links to the NFPA and rules and such. So that's what we got.